Welcome to the Energy, Oil, and Gas module of the Control Systems Fundamentals for Industrial Networking course. The goal of this course is to enable learners to assimilate the information presented in further training courses, such as managing industrial networks with Cisco networking technologies. This module will introduce you to why the energy utilities industry is moving to a converged network and look at design considerations for an energy utilities networking environment. In this module, we will explain the high-level elements required in the mining space, identify mining standards and protocols, and describe network requirements and IT considerations of availability, redundancy, wireless connectivity, and secure remote access for the mining industry. In this lesson, we will present the high-level elements and network components required in the mining space. Mining is the process of extracting natural minerals from the earth. Natural minerals such as gems, metals, coal, grave, and clay are valued in commercial markets of today, but cannot be produced or grown by man. To access these goods, the natural minerals must be mined from the earth. There are three main phases to mining that can benefit from a modernized network that enhances communication, automation, and overall safety and security. Extraction. In the extraction process, safety measures are essential. This process includes blasting through earth and hauling large chunks of mixed debris and minerals away from blast sites. Work done in the extraction processes must be planned, controlled, and precisely executed to minimize incidents. Transportation. In the transportation process, logistics, communication, and security are priorities. This process includes hauling precious materials from the extraction site to the processing plant using trucks, rails, or ships. Distances may vary depending on the operation. Transporting materials must follow a schedule to optimize the arrival of raw materials for processing and must be secure to protect valuable minerals and limit unauthorized access to dangerous extraction and processing sites. Processing. In the processing phase, continuous operations are important. Process steps vary depending on the mineral, but often include separating raw materials from rock and earth and readying the mineral for commercial use. Work done in the processing phase often includes automated devices, controlled procedures, and safety and security measures. The extraction phase is where minerals are found and removed from the earth. In modernizing the mining industry, the following extraction applications may be used: communicating blast events throughout the extraction site, transmitting seismic data to remote controller locations, collecting crush and load data, monitoring vehicle loads, controlling traffic and personnel access in and out of extraction sites, collecting operational, maintenance, and status data from extraction site machinery and devices, and monitoring containment systems, liquid level data in holding ponds, and the status of dewatering pumps. The transportation phase starts at the blast site, where rock fragments are loaded into a vehicle and hauled to a refinery for processing. Processing facilities may be located on or near the mining site, or facilities may be many miles away. Raw materials traveling to on-site processing facilities often travel by conveyor belt or truck. If traveling off-site, materials will go by rugged fleet trucks, railway, or by barge or ship. In modernizing the transportation phase, the following applications may be used: communicating with transport vehicles to determine load quantities, departure and arrival schedules, and location status. Identifying transport vehicles and monitoring access to excavation and processing sites for security purposes. Sending and receiving data to control unmanned vehicles. And collecting equipment and device data to monitor maintenance and vehicle performance. The processing phase takes place in a facility similar to manufacturing. The processes vary depending on the material being processed. However, many of the automation equipment and industrial protocols found in this phase match those located in a manufacturing plant. Often, processing includes crushing rock fragments and separating rock and earth from raw material. When processing metals, such as copper or gold, heat may be applied to reshape raw materials into bricks, ropes, or balls. In modernizing the processing phase, the following applications may be used. Communication with machine operators throughout the site. Controlling devices that run crushers, conveyor belts, and filtration equipment. Identifying and separating mineral fragments from rock and earth fragments. Deploying video surveillance to monitor materials at critical processing points. Collecting operation performance data and controlling devices remotely from a central location. And limiting access to hazardous processing areas to authorized personnel only. In this module, we will explain the high-level elements required in the mining space, identify mining standards and protocols, and describe network requirements and IT considerations of availability, redundancy, wireless connectivity, and secure remote access for the mining industry. In this lesson, we will present the high-level elements and network components required in the mining space. Mining is the process of extracting natural minerals from the earth. Natural minerals such as gems, metals, coal, grave, and clay are valued in commercial markets of today, but cannot be produced or grown by man. To access these goods, the natural minerals must be mined from the earth. There are three main phases to mining that can benefit from a modernized network that enhances communication, automation, and overall safety and security. Extraction. In the extraction process, safety measures are essential. This process includes blasting through earth and hauling large chunks of mixed debris and minerals away from blast sites. Work done in the extraction processes must be planned, controlled, and precisely executed to minimize incidents. Transportation. In the transportation process, logistics, communication, and security are priorities. This process includes hauling precious materials from the extraction site to the processing plant using trucks, rails, or ships. Distances may vary depending on the operation. Transporting materials must follow a schedule to optimize the arrival of raw materials for processing and must be secure to protect valuable minerals and limit unauthorized access to dangerous extraction and processing sites. Processing. In the processing phase, continuous operations are important. Process steps vary depending on the mineral, but often include separating raw materials from rock and earth and readying the mineral for commercial use. Work done in the processing phase often includes automated devices, controlled procedures, and safety and security measures. The extraction phase is where minerals are found and removed from the earth. In modernizing the mining industry, the following extraction applications may be used. Communicating blast events throughout the extraction site. Transmitting seismic data to remote controller locations. Collecting crush and load data. Monitoring vehicle loads. Controlling traffic and personnel access in and out of extraction sites. Collecting operational, maintenance, and status data from extraction site machinery and devices, and monitoring containment systems, liquid level data in holding ponds, and the status of dewatering pumps. The transportation phase starts at the blast site, where rock fragments are loaded into a vehicle and hauled to a refinery for processing. Processing facilities may be located on or near the mining site, or facilities may be many miles away. Raw materials traveling to on-site processing facilities often travel by conveyor belt or truck. If traveling off-site, materials will go by rugged fleet trucks, railway, or by barge or ship. In modernizing the transportation phase, the following applications may be used. Communicating with transport vehicles to determine load quantities, departure and arrival schedules, and location status. Identifying transport vehicles and monitoring access to excavation and processing sites for security purposes. Sending and receiving data to control unmanned vehicles. And collecting equipment and device data to monitor maintenance and vehicle performance. The processing phase takes place in a facility similar to manufacturing. The processes vary depending on the material being processed. However, many of the automation equipment and industrial protocols found in this phase match those located in a manufacturing plant. Often, processing includes crushing rock fragments and separating rock and earth from raw material. When processing metals, such as copper or gold, heat may be applied to reshape raw materials into bricks, ropes, or balls. In modernizing the processing phase, the following applications may be used: communication with machine operators throughout the site, controlling devices that run crushers, conveyor belts, and filtration equipment, identifying and separating mineral fragments from rock and earth fragments, deploying video surveillance to monitor materials at critical processing points, collecting operation performance data and controlling devices remotely from a central location, and limiting access to hazardous processing areas to authorized personnel only. In order to connect all the mining phases together into one unified solution, the connected mine should contain the following elements: seamless communications between central control centers and remote operating teams allow for real-time decision-making and collaboration between remote experts and field technicians. Enhanced health and safety allows mining operators to accurately locate personnel and assets and enables real-time monitoring of environment conditions. Integrated logistics, maintenance, and operations allows operators to track assets, detect issues, and administer predictive maintenance. Remote operations enable field personnel access to the network for mobile devices, allow for remote collaboration, and reduce the number of necessary site visits. And real-time operation and automation improves production operations, minimizing the product time to market. Let us review each phase of the mining operation, taking into consideration how unique mining characteristics may impact how a unified network is deployed. At the extraction site, considering the type of site and operation before settling on a network approach is important. Open pit and underground sites each have their own characteristics and unique set of challenges. Open pit. Open pit mining is the process of digging out abundant rocks or minerals found close to the surface of the earth. The removal of these rock and mineral deposits form an open pit. Characteristics of an open pit include machinery and transport systems are constantly moving as pits. Deep and exhausted areas are abandoned for new sections. Transportation routes are complicated and often not static due to the constant deepening and widening of the pit. Machinery and devices are outdoors, therefore exposed to varying weather conditions, and water control is necessary to keep the pit from becoming a lake. Network approaches to open pits include high-performing wireless connectivity accessible by machinery and personnel both in and out of the pit. Underground. Underground mining is the process of creating a series of tunnels and underground rooms to access rocks or minerals found deep beneath the surface of the earth. Characteristics of underground mining include communication for underground mining is a challenge because assets are hard to reach deep underground. Space for transporting minerals, tunneling machinery, and people are tight. Moving assets requires planning. The use of machinery in enclosed underground spaces makes exhausted ventilation systems a requirement. Underground conditions are often wet or damp and may require the use of water drainage systems. Network approaches for underground mines are commonly a mix of robust wired and wireless connectivity. Mining transportation networks use many of the same solutions as intelligent transportation systems, or ITS. Depending on the distance to the processing plants, trucks, rail, or ships may be used, and each has their own networking challenges to consider. Some considerations for connected truck or fleet vehicles include sensors to avoid overloading and monitor vehicle performance are necessary to prevent unnecessary maintenance. For example, sensors that continuously monitor tire pressure could help extend the life of costly truck tires. onboard cameras and video services to provide expanded visibility for truck drivers. Video cameras help drivers avoid collision in situations when an obstacle is in a side or rear view blind spot. High-precision GPS units to track vehicle positions and assist the driver with navigation. Mobile network access to provide en route drivers and vehicle devices the ability to communicate in remote areas. Scheduling and dispatching solutions to maximize continuous operations and avoid travel delays that impact extraction or processing schedules. And surveillance and security measures to protect valuable raw materials on board. At the processing site, materials are subjected to a series of milling and refining processes such as crushing, grinding, screening, and leaching. Processing site networks use many of the solutions typically found in manufacturing. Network considerations at the processing plant include the following. Devices need to be controlled from a central location. Operational data needs to be collected and utilized to optimize processing. Communication needs to be available throughout the plant site. Network components need to be rugged to withstand dust, blasting, and vibrations, extreme temperatures, and in many cases, outdoor weather conditions. And security measures need to be put into place to limit access to the plant site and to hazardous locations within the site. The connected plant architecture is a solution that improves operational efficiency by integrating key expertise through voice, video, and access to applications, increasing data collection by extending sensor networks and adding location determination, and reduces cost by relying on standard networks. The benefits of a unified mining solution include: in a smart and connected mine, a unified solution will maximize operations with real-time automation and controls. In a connected mine, a unified solution will maximize safety in the extraction phase while reducing the risk involved by monitoring mine environmental conditions. In mining, processing, and transport operations, a unified solution will enable a variety of digital strategies through the use of a reliable and secure wireless network. To ensure safe mining operations, a unified solution will utilize monitoring systems to determine component status and predictive maintenance solutions to enhance operational integrity. In this lesson, we will present mining standards and protocols. The nature of mining is dangerous. In the extraction phase, miners use explosives to extract materials and are exposed to tight spaces where air quality contains particles of dust and debris. In the processing phase, heavy rock fragments are crushed under enormous pressure, and chemicals and heat treatments are used to refine raw materials. To guarantee the safety of workers, the mining industry recognized the need to develop and consent to a globally acknowledged set of standards. The standards are created by the following regulatory organizations: the American National Standards Institute, or ANSI, is the U.S. representative to the International Organization for Standardization, or ISO. Some ANSI standards that apply to mining include confined spaces safety standards, protective clothing standards, and machine risk assessment standards, among others. The International Society of Automation, ISA, is a nonprofit global organization that sets the standards for industry automation, including environmentally sound practices related to the extraction and processing of minerals. National Fire Protection Association, or NFPA, is a national organization charged with preventing fire and other hazards from impacting the environmental quality of life. Mining-related NFPA standards include fire prevention and control in underground mines, surface mines, and in mineral processing facilities. Worker safety is a major focus in the mining industry. In order to prevent injury, disease, and deaths from mine-related hazards, such as falling rock and debris, hazardous mineral dust, and prolonged intense exposure to noise, labor safety standards are set and promoted by the following associations. The Occupational Safety and Health Administration, or OSHA, is a U.S. Department of Labor administration dedicated to assuring safe and healthful working conditions by setting and enforcing standards and by providing training and education. The Mine Safety and Health Administration, MSHA, is a U.S. Department of Labor administration dedicated to promoting a safe and healthful workplace for miners by mandating miner safety training, promoting mine-related hazard and disease awareness, and providing technical support to the mining industry. ATEX, derived from the French term atmospheres explosives, consists of two European directives created to protect workers who are exposed to potentially explosive environments. To review, ATEX classifications are divided by areas where an explosive mix of material is always or often present, such as areas in a processing plant where chemicals and extreme pressure are continuously used to refine raw materials. Areas where an explosive mix of materials is sometimes present, such as occasional site blasting where a controlled use of explosives are often used to excavate materials. Areas where an explosive mix of materials is seldom present but can happen accidentally, such as an underground excavation site, where poorly ventilated areas may collect an explosive mixture of gases and vapors. The Dangerous Substances and Explosive Atmosphere regulations mandate that equipment and safety control systems are certified for explosive atmospheres and marked accordingly. Similar to the oil and gas industry, a variety of communication standards are used at all levels to control the mining process, such as Ethernet IP, used together with CIP sync and CIP motion technologies, enables real-time control for motion control applications. Profinet provides a fast and reliable way to access powerful diagnostic information and troubleshoot issues quickly. Profibus links control systems with field devices such as sensors and actuators. This protocol enables a consistent data exchange with higher-ranking communication systems, which supports the automated mining process as well as in-motion control and safety-related tasks. Modbus, a serial communications protocol, is often used in connecting industrial electronic devices. Modbus enables communication for up to 240 devices on the same network. Modbus is commonly used to connect a remote terminal unit, or RTU, with supervisory control and data acquisition systems, also known as SCADA. Some mines have introduced Modbus TCP to take advantage of cost-efficient Ethernet network cards, switches, routers, and cabling. HART provides intelligent networking control for plant-wide wireless mesh networks. Interfaces from 4 to 20 milliamps control circuits and is used in all phases of mining. Opencast mining uses Profibus DP, or decentralized peripherals, and Profibus PA, process automation for field devices. Profibus connects the remote I/O devices and control units to the PLCs. Profibus PA is often used in areas that are highly explosive because Profibus PA is a process-oriented protocol used to run devices that are engineered for safety, such as sensors, metering devices, monitoring stations, and controllers. For example, transporting coal from within a mining operation deep underground is a hazardous process and requires very precise timing. This process often involves moving materials up a vertical shaft with a tower at the top and a mechanism to control the movement of containers carrying the coal up the mine shaft. For safety and efficiency, the exact location of each container must be known at all times. A very high degree of control is needed to position these containers precisely at their respective docking stations. An automated system controls and synchronizes this movement and requires fast, reliable communications among field and control devices. Network links are used to interface the robust Profibus PA network connecting the underground field devices to the Profibus DP network. The speed of the Profibus DP network is needed as a backbone for sending status and control messages to and from the control devices and PLCs and their remotely located control applications. Highway Addressable Remote Transducer, or HART, protocol is used for process data gathering and monitoring, used to connect sensors to monitor mining conditions such as temperature, vibration, and pressure, can be used in harsh environments and where mobility is required, and control data gathered in the field is transmitted to the mine control room. HART can implement a wireless plant-wide network using a wireless mesh architecture based upon 802.11 standards. By using wireless mesh, HART provides self-healing capability within the wireless network as well as resistance to interference. In this lesson, we will present IT considerations for the mining space. IT requirements for the mining industry can be compared to oil and gas industry requirements. Both industry networks cover multiple phases, including an extraction, transportation, and processing phase. Each phase has unique characteristics including hazardous and remote operations, mobile components, and a variety of automated processes. Like oil and gas, the mining industry requirements include network availability and redundancy to support a productive and safe operation, secure remote access for mobile and remote operations, wireless solutions for connecting devices at extraction sites, and wireless solutions for connecting devices at extraction sites. In addition, mining networks also need to support trucking and coordination with rail and shipping, and therefore share the same embedded transport solutions as intelligent transport systems. In distribution and management networks, the components for mining extraction, transportation, and processing operations are similar to those found in manufacturing. However, the components can be used in a variety of different applications. Supervisory control and data acquisition and distributed control systems transmit data from IEDs and sensors to a control center for analysis. If action needs to be taken, DCS and SCADA systems can be used to control the process remotely. IP cameras are connected by a wired or wireless network and are widely used in all phases of the mining operation to secure facility perimeters and monitor operations. Instrumentation and meters are used to measure volumes, such as ensuring a consistent amount of raw material is loaded into each rail car at train loadouts. AC drives adjust the speed and torque of standard AC motors found in equipment, such as ventilation systems and conveyor belts. Sensors detect movement, pressure, levels, and flow in a variety of mining applications, such as sensors on a reclaimer detecting pile edges as reclaimers retrieve bulk materials from stockpiles. PLCs with human interfaces control segments of the automation processes, such as controlling the vertical or rotational movement of stackers as the stackers arrange raw material into stacks or piles. Network reliability in mining is not only critical for operational goals, but reliability is also critical to the health and safety of mine workers. If the network fails, lost connectivity is costly due to delays and also potentially hazardous. In the extraction phase, a network failure could cause extraction schedules to fall behind, but in terms of safety, communication may be cut off from workers operating deep underground. Sensors programmed to detect hazardous levels of dust, explosive gas, or vapor may not be able to transmit warnings. Systems used to track worker positions may fail to report someone too close to a blast site. In the transportation phase, a network failure could cause shipping delays, but in terms of safety. Location of vehicles cannot be monitored and therefore may pose issues with traffic control within the mine and surrounding areas. Failure to read sensors that monitor weight and volume may cause vehicles to be overloaded and operate in a potentially hazardous manner. In the processing phase, network failures may cause costly processing production delays, but in terms of safety, machinery used to mix chemicals and crush rocks under extreme pressure may fall out of synchronization, causing potentially explosive and hazardous conditions. For these reasons, mining networks must be carefully managed and controlled to maintain the availability and stability. Mining sites are becoming increasingly more networked. Due to the harsh environments, changing device positions, and remote underground locations, real-time wireless communications are often used to transmit data, voice, and video packets across the network. In addition, handheld mobile devices used to control equipment and processes throughout a mining site are becoming more popular. While these network advancements improve mining efficiently, advancements also open the mining industry up to potential security risk. Mining networks need to take into consideration additional security measures, such as firewalls used at the DMZ for securing the field network from the corporate network, VPN access used to provide remote access for technicians in the field to process status information, strong encryption for securing wireless communication from field devices to the control network and corporate network as required, and port security on access points via 802.1x to authenticate users to the network. Safe and efficient mining operations expect devices, equipment, and personnel to function in outdoor weather conditions, extreme heat, and in close proximity to extreme shock and vibration. Vibrations caused by mining blasts, rough road conditions, and moving heavy rock through processing can be passed on to devices and may damage or destroy equipment. In order to guarantee mechanical stability and offer reliable operation under these conditions, high-performance, ruggedized network equipment should be used. Network equipment needs to pass a variety of performance and certification testing, such as the International Electrotechnical Commission, or IEC, certification test, to ensure normal functioning under mining environments. Cisco Industrial Ethernet 3010 series switches comply with the operational shock and vibration standards displayed. Environmental operating ranges should be noted when selecting network equipment for implementation. When mining materials such as copper or gold, a process known as smelting is used to liquefy the metal, extracting the metal from rock and earth. The extreme temperature inside smelting plants can be up to 55 degrees Celsius. This operating environment is harmful to most electronic devices. Maintaining network quality under such conditions is critical. Therefore, environmental operating ranges should be noted when developing a network approach. Based on which phase of the mining process is being supported, there are several common network topologies that are used. In areas of the extraction and processing phase where there are more automation processes, ring and redundant star topologies are common. In the transportation phase and in areas of the extraction phase where active sites and landscapes change frequently, wireless mesh technologies are common. The network topology selected for the wired and wireless sensor network largely depends on the area that needs to be covered. Considerations like data redundancy or energy optimization needs to be taken into account. Every network topology has personal advantages and disadvantages, but in cases like the mining industry with many phases, such as extraction, transportation, and processing, a hybrid of topologies are frequently in place. Wireless local area networks are ideal for mining sites because WLANs can cover large areas and can accommodate the many moving elements within the process. In most cases, wired topologies are not possible. Continuous digging that changes the landscape would require the network topology to change and expand often. WLANs can be designed to transmit data, voice, and video packets in a harsh and rugged environment. WLANs are also flexible to changing landscapes because multiple APs can be installed to expand a Wi-Fi mesh network. Nodes in a mesh or partial mesh topology automatically and autonomously establish the network. In addition, self-configuring networks can detect the presence of mobile nodes, such as Wi-Fi, voice over IP handsets, and will automatically incorporate the nodes into the network. If a node fails, the self-healing feature will connect to all possible surviving nodes by other available links. Delays may occur if the re-established network covers more distance than the original. Miners with Wi-Fi enabled handheld devices, transportation systems, and traveling machinery can move from one area to another within a mesh network without losing connectivity. Through the use of WLAN, a single mining communication network can support a broad range of applications such as real-time video feeds for remote expert collaborations, transportation vehicle tracking, security surveillance to ensure workers are cleared from blast sites, access control to monitor mine exit and entrance activities, and mining management software for collecting status information from HART sensors. Developing a site wireless profile approach for underground mines presents several challenges. Underground mines consist of a series of tight tunnels broken by larger underground rooms and are often deep underground. Underground tunnels are constantly changing. Tunnels grow longer and new tunnels are created. Environmental characteristics of underground tunnels, such as vibrations and constant moisture, are hard on wireless equipment. Safety is critical and power outages occur often, so communication must remain available through backup systems. Long tunnels make supporting a real-time data transfer difficult. To combat these challenges, an underground wireless network must provide a stable and reliable infrastructure that is easy to deploy and relocate. Mesh systems should be deployed to cover expanding areas and to provide redundant paths that can protect network connectivity if rock or debris blocks one of the paths. In addition, devices need to be rugged and the system needs to be operable through the use of battery power when necessary. Successful installation in an active underground mine requires long-distance network access for voice, location tracking, and video monitoring. Throughout the mine, wireless mesh nodes should be secured to the tunnel supports and powered by a battery backup system. Individual miners may carry wireless Wi-Fi voice-over IP handsets that provide voice connectivity to the central office, allowing them to make repairs or supply requests. Wi-Fi voice-over IP handsets also allow for tracking the location of a miner within the mine. IP-based cameras are also used to remotely monitor key sections of the mining operation. Both open pit and underground mining sites cover a lot of ground. Getting from a surface-level office to a location in the mine may take time and planning. Most likely, safety precautions will also need to be taken, such as putting on personal protective equipment. With the use of IP cameras, location and asset beacons, and measurement instrumentation wirelessly connected through the mining site, managers and mining experts can more cost-efficiently observe mining activities from anywhere. Solutions such as expert collaborative operations exist to allow a mining operation the ability to share resources via high-quality video and desktop sharing across multiple mines. Video from rugged cameras on vehicles or handheld devices could be shared to the central office using UC-TP. Experts such as geologists, process analysts, chemists, metallurgists, engineers, and equipment specialists and technicians, among others, use the video to collaborate on mine activity. With wirelessly connected cameras and devices, these experts do not have to be in the mine or even in the same room to discuss operational issues. For some especially dangerous mining operations, workers can stay out of harm. IP cameras and remote control functionalities allow operators to maneuver equipment from a safe distance. Wireless technology is especially important in mining transportation systems where vehicles, rail cars, and shipping barges are on the move. A connected vehicle allows safety and control applications to monitor the status and location of the vehicle. Often, transport vehicles utilize WLAN connectivity to transmit location and status information for tracking and maintenance purposes. Cellular service allows drivers to maintain voice communication while en route between extraction and processing sites, while WLAN mesh networks deep within mines enable phone services in areas that are too remote for cellular service. Off-site, through cellular service, a GPS provides instructions for navigating drivers around traffic and detours to and from the extraction site. Mining operations often use wireless sensors to monitor the status of transport vehicles and report status details back to management. While WLAN has many benefits, WLAN also has several limitations. On sites as large as a mining site, multiple antennas need to be installed. For a typical plant, this installation is fine. However, on mining sites, the earth is always changing due to expanding pits and extended tunnels. In order to stay connected, antennas or APs may need to be moved or added periodically. To combat these challenges, cellular networks may provide a solution. Private long-term evolution, or LTE, networks have been used to enable technology for vehicle autonomy in mines. A truck holding an LTE-capable router can connect to an LTE access network for application control and monitoring. Private LTE networks are cost-effective and can be implemented across long distances with only a few towers and minimal backhaul. Additionally, private LTE networks can be run either by the enterprise, a systems integrator, or a mobile service provider. This process provides a stable network that ensures that autonomous haul trucks are always connected and operating at full capacity. In this module, we have seen that there are three main phases to mining that can benefit from a modernized network, including extraction, transportation, and processing. Network approaches for mining can use both wired and wireless connectivity. Protocols in use in the mining industry are often proprietary at this time. The mining industry is regulated by standard organizations such as ANSI, ISA, NFPA, and ATAX. The network architecture in the mining space include IT requirements such as availability, redundancy, wireless connectivity, and secure remote access. Mining network components must be selected to operate in harsh and variable environmental conditions. Wireless networking in the mining industry network will be used extensively due to environment and mobility requirements.